So we move on to homogeneous equations with constant coefficients. So recall a linear homogeneous equation is anx, nth derivative, an minus 1 of x, n minus first derivative, all the way up to a1 of x, the first derivative, a naught of x, and y equals 0. It is key to note that the right-hand side has to be 0, or else the equation is a non-homogeneous equation. So what is a linear homogeneous equation with constant coefficients? So here an of x is a number, let's just say an minus 1 of x is simply a number, an minus 1. a1 of x is a number, we'll call it a1. a naught of x is also a number, we'll call it a naught. So what is the consequence? The equation becomes an y raised n plus an minus 1 y raised n minus 1 all the way up to a1 y prime plus a naught y equals 0. So let's look at an example. A first order homogeneous equation with constant coefficients. First order, so we need to start with y prime. So we'll have 3y prime plus 2y equals 0. If you look at an, which is a1 of x, and a naught of x, both of them are numbers. In other words, they don't have any x terms or terms involving the independent variable. And we could use one of the methods that we already know, such as separable equations, or we could use the integration factor approach to find a solution to a first order homogeneous equation with constant coefficients. Now we look at a second order homogeneous equation with constant coefficients. And a good example would be 4y double prime minus 3y prime plus y equals 0. So if you look at the coefficients, it's 4, negative 3, and 1 there. 1 times y is y. So that is a second order homogeneous equation with constant coefficients. So a2 is 4, a1 is negative 3, and a0 is 1. And I could extend this and keep on going. For instance, a fourth order homogeneous equation with constant coefficients would be 5 fourth derivative of y multiplied by 2 second derivative minus 3 the first derivative plus y equals 0. Here, that's a constant, that's a constant, that's a constant. The constant there is 1. So A4 is 5. A3 is missing, so it has to be 0. You don't see a third derivative here. A2 is minus 2. A1 is minus 3. And A0 is 1. So in order to solve a homogeneous equation with constant coefficients, we have a nice approach. And I'm going to explain the approach first before I do any examples. So what is the approach? We'll start with the second order equation because we already know how to solve homogeneous first order linear equations. We have the method of separable equations, we have substitution, we have integration factor-based method. So we have all of that. So we're going to move on to solution to a second order homogeneous equation. So I'm going to write a general form. I could simply say A y double prime plus B y prime plus C y equals 0. So that is a second order homogeneous equation. The constants are A, B, and C. A key step is to find what we call the auxiliary equation. The auxiliary equation is simply A multiplied by some expression. I'll use M. And you see the second derivative here, so I'm going to put 2. B multiplied by y. I see the first derivative there, so I'm going to multiply it by m raised 1. Plus C, I don't see a derivative there, it's just y, so I'm going to multiply by m raised 0. So the equation becomes am squared plus bm plus c equals 0. And that equation should look familiar to you. The above equation is a quadratic equation, and we all know how to find the solution to that quadratic equation. Now, before we go there, why do we have to plug in that m and find the auxiliary equation? So here is the reasoning. For a second order linear homogeneous equation with constant coefficients, a solution is y equals e raised m times x. That is theoretically proven. So if we have a second order linear homogeneous equation with constant coefficients, then a solution is definitely going to be of the form y equals e raised mx. That said, if you look at the quadratic equation has two roots. i.e. there are two numbers and they could be real or they could be complex. Which satisfy am squared plus bm plus c equals 0. In other words, if we plug in either of those numbers, then the right-hand side would be either of those numbers. In this equation on the left-hand side, the right-hand side will be satisfied. In other words, we would get 0. So how do we find the two numbers? So all we have to do is to find the roots using the quadratic formula. So minus b plus or minus square root of b squared minus 4ac divided by 2a. And there are three cases that we will encounter typically with a quadratic equation. The first case is that you have real and distinct roots. Distinct means the roots do not look the same. So the first root would be m1 minus b plus square root of b squared minus 4ac divided by 2a. And the second root is minus b minus square root of b squared minus 4ac divided by 2a. And if you recall from algebra, b squared minus 4ac is called the discriminant. And for an equation to have, for a quadratic equation, to have real and distinct roots, b squared minus 4ac has to be bigger than 0. In other words, whatever that is inside the square root must be a number bigger than 0, and it has to be a real number. If that is satisfied, then the equation will have real and distinct roots. So since the roots are distinct, we have m1 as one root and m2 as the other root. Since m1 and m2 are two roots, y1 equals e raised m1x and y2 equals e raised m2x are two solutions to the DE. So if we go back up here, I already suggested that if we have a linear homogeneous equation of second order with constant coefficients, a solution would be y equals e raised mx. And what is that m? M is any value that would satisfy the quadratic equation am squared plus bm plus c equals 0. So the two solutions are y equals e raised m1x and y1 equals e raised m1x, and y2 equals e raised m to x. So this would mean, by superposition principle, y equals c1 e raised m1x plus c2 e raised m to x is a general solution to the homogeneous dE with linear constant coefficients. I should say linear homogeneous dE. Great. Now here c1 and c2 are arbitrary constants. And that is case 1. So case 2 is real and equal roots. What do I mean by that? If b squared minus 4ac is equal to 0, i.e. the discriminant is 0, then m1 would equal minus b plus square root of 0 divided by 2a, and m2 would equal to minus b plus, minus square root of 0 divided by 2a. And we will get m1 is equal to minus b over 2a, and m2 is equal to minus b over 2a. Notice the roots are the same. They are real numbers, but they are the same. Now you may say, we'll take the same approach that we did previously and say, since we have two roots, y1 equals e raised m1x and y2 equals e raised m2x are two solutions. But the key thing to note here is that the roots are the same. If the roots are the same, this solution and that solution will be the same because m1 equals m2. So we didn't do anything special here. We need to find that second root. If we don't have that second root, we can't find a solution. This is where the reduction of order comes into play. So we know for sure that y1 equals e raised m1x is a solution to the dE. Now, using reduction of order, a second solution can be found. What do I mean by that? Recall the reduction of order formula as y2 equals y1 integral e raised negative integral p dx divided by y1 squared multiplied by dx. And that integrating factor, e raised negative integral p dx, comes from the original equation. So going back to the original dE, a2 y double prime, or sorry, I used a, so a y double prime plus b y prime plus c y equals 0. I'm going to divide by a on both sides. And we have to make a direct comparison in reduction of order to y prime plus py plus py prime plus qy equals 0. And if I compare, I'll find p to be b over a and q is c over a. Now, we don't want b and a in the solution, rather we want the root in the solution, because if we specify the root, then, or if we find the root, then we can make use of the root to find the solution. So, since the root m1 is minus b over 2a, multiply by negative on both sides, negative m1 equals b over 2a, which would imply b over a is negative 2m. I'm going to take that and plug it in p. That would conclude that p is simply negative 2m1. I'm going to take that p and plug it in there and integrate. So the second solution is y2 equals y1 integral e raised negative integral negative 2m1 dx divided by y1 squared dx. But we know y1 equals e raised m1x is a solution to the dE. This would mean y2 would equal to e raised m1x integral e raised 2 m1 integral dx divided by e raised m1x squared dx. In the numerator, when I integrate dx, I would get x, so the numerator becomes 2m1x. The denominator, using the properties of exponential, would also become 2m1x dx. Those two would get cancelled. And I would have y2 equals e raised m1x integral dx which would give us e raised m1x multiplied by x. Since m1 and m2 are the same, we will let m1 equals m2 equals sum m, because the roots are the same. So the second solution is e raised m times x multiplied by x. So the two solutions to the linear homogeneous DE with constant coefficients is y equals c1y1 plus c2y2. That is the superposition principle. So if we have two linearly independent solutions, then the general solution is a linear combination. This is what we call the linear combination of the two solutions. So the solution here would be c1 e raised mx plus c2 x times e raised mx. So that will be the general solution for the case where the two roots are equal and they are real. And this is what we call the repeated root case. Suppose the discriminant b squared minus 4ac is less than 0. This would mean square root of b squared minus 4ac is complex. Why? If b squared minus 4ac is less than 0, the square root of a negative number is imaginary or complex. That's what complex means. And we should also note that if the roots are complex, this is an important remark, they always appear in conjugate pairs. In other words, if one root is a plus ib, then the other root would be a minus ib. Or if I use the standard notation, I should just call it alpha and beta. Sure, we can plug this in the differential equation, but we would have complex numbers in the differential equation, and we don't want that. So what we're going to do, let's just go ahead and plug it in and see what happens. I will save what I wanted to say until later. So since they are conjugate pairs, Since they are not the same, y1 would be e raised m1x, that would be one solution. We can write it as e raised alpha plus I times beta multiplied by x, which should be e raised alpha x plus I beta x, which would simply be alpha x times e raised I beta x. That is using the properties of exponential. The second solution would be e raised m2x. So we have e raised alpha minus I beta x. So e raised alpha x minus I beta x, which should be e raised alpha x multiplied by e raised negative I beta x. Great. So we have the two solutions. So the general solution to a linear, homogeneous DE with constant coefficients and complex roots is simply a linear combination of y1 and y2. Again, superposition principle. So we would have y equals c1 e raised alpha plus I beta x plus c2 e raised alpha minus I beta x, which we write it as c1 e raised alpha x multiplied by e raised I beta x plus c2 e raised alpha x forgot to put the parentheses. And we can see e raised alpha x is common between the two terms, so I could pull that out and write it as c1 e raised I beta x plus c2 e raised minus I beta x. And we end up having complex numbers in our solution, and we don't want to have complex numbers. We somehow have to get rid of the complex numbers. So for the time being, I'm going to assume c1 and c2 equals 1, and later on I'm going to throw in the constants at the very end. So if c1 and c2 are equal to 1, then y would equal e raised alpha x multiplied by c1 e raised I beta x, e raised I beta x plus e raised minus I beta x. And going back to Calc 3 or Calc 2, recall Euler's formula. What does it say? E raised I beta x is cosine beta x plus I sine beta x. Likewise, e raised minus I beta x is cosine beta x minus I sine beta x. So if I add those two equations, e raised I beta x plus e raised minus I beta x would equal cosine beta x plus I sine beta x plus cosine beta x minus I sine beta x. Those two would get cancelled, and I would simply have 2 cosine beta x. And if I subtract the two equations in Euler's formula, I would have cosine beta x plus I sine beta x minus of cosine beta x minus I sine beta x. So I would have cosine beta x plus I sine beta x minus cosine beta x plus I sine beta x. Those two would go away, and I would have 2I sine beta x. Why did I find this? Well, going back here, e raised I beta x plus e raised negative I beta x is equal to 2 cosine beta x. So the first solution, which is right here, e raised alpha x multiplied by 2 times cosine beta x. So that is our first solution. Now, how did we get that first solution? We ended up setting C1 and C2 equal to 1. Now, what if I set C1 equals 1 and C2 equals negative 1? You may say, well, why do you have to pick this? Why can't you pick C2 as 1 and C1 as negative 1? You would get the same answer. So, and we can't pick C1 to be negative 1 and C2 to be negative 1 because we will end up having linearly dependent solutions. So this would be the only other case. So if I said C1 equals 1 and C2 equals negative 1, the second solution is y2, and I'm simply going to plug in 1 and minus 1 up here. I would have e raised alpha x multiplied by e raised I beta x minus e raised minus I beta x. But from Euler's formula, I know that that is equal to that term. So e raised alpha x multiplied by 2I sine beta x. So the solution is 2I e raised alpha x sine beta x. So now we have two solutions for a second order linear homogeneous differential equation. So since y1 equals e raised alpha x cosine beta x and y2 equals, there is a 2i e raised alpha x sine beta x are two solutions to a linear, not homogeneous dE with constant coefficients the general solution is y equals c1y1 plus c2y2. So that would be c1 to e raised alpha x cosine of beta x plus c2 multiplied by 2i e raised alpha x sine beta x. But 2c1 is a constant. 2ic2 is another constant. So I could simply write this as c3 e raised alpha x cosine beta x plus c4 e raised alpha x sine beta x. We have e raised alpha x in common, so y is equal to e raised alpha x multiplied by c3 cosine beta x plus sine beta x. So what is our conclusion here? If we have a second order linear homogeneous equation with constant coefficients, we need to find the auxiliary equation and we need to find its roots. And if the roots are real and distinct, the solution would end up being that. If the roots are repeating but real, the roots are real but they repeat, then the solution would be that. If the roots are complex, then the solution is that. So the entire key to finding the solution is dependent on the roots of the auxiliary equation. So the very first step in solving a second order linear dE is to find the auxiliary equation. And when I do the examples, you would see how to find the auxiliary equation, and we can make use of a calculator to find the root. We don't want to constantly use the quadratic formula to find the roots. These days we are technically advanced, so we can make use of a scientific calculator to find the roots.